This video is meant to provide an introduction to what we call enumerative combinatorics, which is a very fancy way to say that we're counting things. The first problem we'll consider is one that has a relatively small answer, so that we can answer the question by simply making a list of all the different possibilities here. In the problem, we assume that there are 4 people at a party, so you should know that these are the only 4 people at the party, and 2 prizes are given away to the people in attendance. And the question is, in how many different ways could those prizes be awarded? This question is intentionally vague, and so it's a worthwhile exercise to try to answer this and think about what you're assuming about the scenario as you answer the question. And then once you've thought about it, maybe unpause the video and we'll talk about some different assumptions and how the answer changes based on what the assumptions we make. So here are 2 questions you might have identified as being ambiguous in the problem. One is that we're not told whether it's possible for the same person to win both prizes, and that would be directly related to how the prizes are being awarded, which we don't know. And so that was something we would need to know to pin down an answer. And then the second question, which is more subtle perhaps, is that are the prizes different? In other words, if one prize is a $5 bill and the other prize is a new car, then when you came home to report what happened at the party, you would report it quite differently if it was the case that just 2 people won $5 bills, or if one person won a $5 bill and the other person won a car. So the way you would report it would be different in those situations. So if the prizes are dramatically different, then it certainly makes a difference in how you would report the outcomes. So the answer to these questions are just yes or no, and so that means that depending on your combination of answers to these questions, there are 4 different kinds of problems that we could be looking at here. So let's just look at each one. So if the 2 prizes are considered the same, so in other words, you have 2 prizes, but you get an envelope with a $5 bill in it, and there also is a rule that the same person cannot win both, which is sort of what would happen if you put the 4 names in a hat and just drew slips of paper out, then the same person wouldn't win both. If that happened, then if you came home from that party and wanted to report who won the prizes, you would just say the names of the 2 people who won. That's the only thing you would have to say. So the order that you said their names wouldn't matter. You wouldn't say the same person's name twice. And so that scenario feels a lot like what we've already studied in this course, where the objects are called sets. A set, remember, is an unordered list of objects, and we don't put the objects in the set more than one time. So what we have here then is a list of all the ways of forming a 2-element set from the set of 4 people who are at the party. And so you can see there are 6 people, 6 possible ways we could do that, but the most important thing here is I'm going to represent those using my curly brackets, and they have all the characteristics of sets, so we might as well represent them as sets. So that's one scenario. Another possibility is that the 2 prizes are different. And so in this case, think very different. Think one prize is an envelope containing a $5 bill, and the other prize is an envelope containing the keys to a new car. So that's quite different. If you came home from that party and wanted to say who won, you would definitely want to distinguish between the 2. So it's much different to say A won the $5 and B won the car than it is to say B won the $5 and A won the car. Right? At least, especially to A and B, those 2 results matter a lot. And so if we wanted to list all of those, I'm going to do it by just making these little strings of letters. So, and you'll see later on, we'll talk about this as sort of filling in the blanks. So I'm going to represent an outcome as just filling in the blanks with 2 letters. And I would have to tell you that the first letter refers to who wins the first prize. So maybe the first letter is who won the car, and the second letter is who won the $5 bill. And if I specify that, then there's no doubt that A followed by B is different from B followed by A, especially if you are one of those 2 people. Other than that, you can see that the different cases here of which 2 people are involved, those really match the sets that I had before. And so all I'm really doing here is I'm considering each of those things that before I called sets, and I'm thinking about the order mattering, so I have twice as many. Now, just for easy reference, it's worth noting that we call these permutations. Anytime we have lists of objects and the order of the objects in the list matter, and we're not allowed to repeat objects, we call that a permutation. And the word is supposed to evoke an image of like physically moving objects around. So the example I always use for this is if you had like a refrigerator magnet letters, an A, a B, a C, and a D, then this is just all the ways that you could put like a little 2-letter word on the refrigerator. I know those aren't all words, but all the ways you could put 2 letters next to each other on the refrigerator. So we'll call that permutations. It sounds like we're just moving things around, and that's what it should feel like. Okay, let's look at a third possibility. So in the third possibility, we'll again assume the door prizes are different. Again, we'll use the same convention of thinking of it as filling in the blanks, where the name in the first blank is who wins the car, and the name of the second blank is who wins the $5 bill. So we're thinking of all the ways of filling in 2 blanks. But in this case, we have a rule that allows the same person to win both. And this is what would happen, say you had a 4-sided die, like a little tetrahedron die, and you rolled that to decide who won the car, and then you rolled it again to see who won the $5 bill. If that's the way you awarded the prizes, then it'd be perfectly possible for someone to win both. It would seem a little greedy for the person with the car to also accept the $5 bill, but it would be possible. And so what you see is I'm representing that in the same way that I did the permutations. The only difference is I'm allowing now the same letter to be used more than once. And so this is a more general case than permutations. There's no restriction here on how many times I use letters. And so in this more general case, I'm going to refer to these objects as ordered lists. So this is a very generic term. Order list meaning the order that I put them in the blanks matters, but that's all I care about. Go for it if you want to use the same letter more than once. As far as the number goes, you can see that all that's happened here is we added 4 things to what we had before, right? So it's exactly the same 12 outcomes we had before, but now there are 4 new things. So it's easy to see how those numbers are the same. I've written these in this sort of array because I want to also point out that this looks like if instead of writing these as filled in blanks, if you imagine for a second that I wrote these as parentheses, letter, comma, letter, right? So if I added more stuff here, notice how this looks like all possible ordered pairs, where the first coordinate comes from A, B, C, D, and the second coordinate comes from A, B, C, D. So with that extra sort of putting the parentheses on there, this looks exactly like the Cartesian product of ABCD cross ABCD. And we learned in our unit on sets that the size of a Cartesian product is just the size of the first set times the size of the second set. So the fact that there are 16 things in here is not surprising at all. It's because we have a 4-element set crossed with a 4-element set. In this unit, we're not going to put the parentheses and the comma in there for a couple of reasons. One, that it takes up a lot of extra space, and secondly, that we want to be able to put more things in than just 2 things in blanks. We want to be able to build strings that are longer than that, and we don't want to have to think about what cross. So we're not going to use the set notation. We'll just keep with the fill in the blanks. So there's one more scenario. In this last scenario, I'm representing these in a weird way, and I'm just going to apologize that this is not really the way that I'm going to represent these when we get to this one. This is the last of the 4 that we're going to tackle, and when we get to that, I will tell you how we'll represent those, and there's a little bit of a backstory to it, so that's why I don't want to get ahead of myself. But in the case where the prizes are the same, so again, like 2 envelopes with $5 bills in them, but it's okay for the same person to win both, then I would just tell you 2 names without caring about the order, and that'll be who won the prizes. And so this would be the list. Either A wins both, or A wins 1 and B wins 1, or A wins 1 and C wins 1, and so on. So it's kind of a mashup of the sets that we had, and then the possibility that people win both. So it's hard to decide exactly how to represent that at this point. So don't take this representation seriously. It's not really what we're going to use. We're not going to really write little strings of letters like that. But we're not going to worry about it until we get to section 5.4. In this general case, we would call these unordered lists because we don't care about the order and we're not worried about using things more than once. Other names for these are multisets because they feel like sets in which you can put things in multiple times. That's a good name. And we'll see some examples later why some people call these bags. So those are all 4 possibilities. So when we write down, we have a new problem to study, we'll write down some examples of the things we're trying to count. And in doing that, we'll have to choose a representation of the things that we're trying to count. Once we start choosing a representation, we're going to ask ourselves, within that representation, does order matter and is repetition allowed? And the yes or no answers to those 2 questions is going to tell us which kind of problem that it is. So as far as our course goes, we're going to start over here. This is going to be section 5.2 of the textbook. Then we're going to use our understanding of from 5.2 to figure out the answers for the case where the things are sets. And then we're going to use our understanding of the sets to figure out what's going on with unordered lists, and that'll be in section 5.4. So that's our roadmap through enumerative combinatorics, and that will keep us busy for the next week and a half.